thermodynamics of this EAPCET series. Okay, and let's wait for 1 or 2 minutes, and yes, the people are joining over here. We'll start exactly with a 1 minute or 1.5 minutes. Okay. Yes, let's start with the class now. Okay, guys, let's go into the topic. The first one, we are going to see what is the meaning of the thermodynamics, and there's some other definition of the points we will see. Like there's some key points what we need to know before going into the chapter. So introduction, if you see, thermodynamics deals with the concept of heat and temperature. We have discussed this heat and temperature in the last class, the thermal properties of matter and thermodynamics, right? Like heat is nothing but it's a energy we have talked, energy, and temperature gives that hotness or coldness of a body, right? And it is a macroscopic science, deals with a bulk system, and does not go into a molecular constituent of matter. Like we are talking about some macroscopic science, right? Now, what is the meaning of system, surrounding, and boundaries? I guess the camera is clear now. The camera is clear, so yes. Okay. Okay, guys. So system is nothing but quantity of a matter or a region in a space which we have taken to study, and the surrounding is nothing but whatever the things which are surrounded by the system is called as surrounding, and boundary which separates the system and the surrounding is called as a boundary. A matter or region outside the system is called as surrounding. A real or imaginary surface that separates system and the surrounding is called a boundary. So three things are important. If you know the three things, then only you can go into the topic: system, surrounding, and boundaries. Right. So the next one is thermal equilibrium. What is the meaning of thermal equilibrium? Thermal. We have learned this topic thermal, like it's dealing with the temperature and the heat. Dealing with the temperature and heat. What is this meaning of equilibrium? That equal, right? Equal, they are saying. Okay, fine. The macroscopic variable that characterize the system do not change in time. Doesn't change with respect to time, they are saying. Right? Wait a minute. Got it? Now, for example, if we take this, consider a gas inside a closed rigid container. So this is filled with gas. The container is there, it's filled with a gas. Container is completely insulated. What is the meaning of insulated? Like nothing can enter inside, nothing can come outside also, and insulated, like it has been covered properly, its surrounding, the value of pressure, volume, temperature, mass and composition that do not change with time. So whatever happens in the surrounding, but anything doesn't affect the gas which is present inside that the container. In a state of thermodynamic equilibrium, a system it is in a state of thermodynamic equilibrium. If nothing is changing in the sense we should understand the point. Pressure, volume, temperature, mass and composition does not change. Like we should consider pressure also, volume also, temperature also, mass also and the composition also. If any one changes, right, I cannot say it is in the thermal equilibrium. It is in the thermal equilibrium. A system is in a state of equilibrium depends on how surrounding and the nature of the wall that separates the system and the surrounding. So that's why I have told the thing, we need to be clear about the system, surrounding and the boundaries. If I am talking about a system, if it is not changing with respect to time, and how it depends on the surrounding and the boundary. What boundaries? Like the container we have taken here, that's called a boundary we are talking. This is system, gas is a system, and the container is a boundary which is like keeping a safe place of the gas inside and which is not getting affected by the surrounding, right? I hope you got clear about the meaning of thermal equilibrium, and we need to know the thing is it doesn't change anything in this pressure, volume, temperature, mass and the composition. It does not change with time. Okay, so the next thing is a thermal equilibrium. If we talk about in a different kind of thing, pressure pressure and the volume of a gas A and B we have taken. So these blue things are gas A and the red things are gas B. And if you see here, like it has been divided in a wall, like insulated, like some wall has been there. Two systems are separated by a adiabatic wall. Adiabatic means like nothing, like no heat can exchange. An insulating wall, adiabatic wall, that does not allow flow of energy, that is heat. I have told that from one to another. So any possible pair of values PA or BA will be in equilibrium with any possible pair of PB and BB. Any possible pairs will be equal, like will be in thermal equilibrium condition, because we have kept adiabatic wall here, so nothing, like no heat can exchange over here, right? So if I take a diathermic wall, which means a conducting wall, so if a conducting wall is there, obviously the heat flow will be there, and I can say it's not in a way. Yes, diathermic wall allows heat energy, like energy from one to another. The system A is in thermal equilibrium with system B. Now what happens? The total system I can say in a thermal equilibrium. Why? Because I have not taken this wall. If I take out this wall, it will go and expose to the surroundings. Got it? Only I have taken the wall between the gas A and B. So if I take it out, this will be the total gas A and B will be in the thermal equilibrium, and this has not been exposed to the surrounding. Okay, I hope it's clear, right? Okay, we'll go for the next one. Got it. So the next one is zeroth law of thermodynamics. So zeroth law, what zeroth law is saying? Two systems in a thermal equilibrium with a third system separately are in a thermal equilibrium with each other. Which means if I talk about Vignesh Sir. Okay, let me take A, B, and this is C. Okay, A, B, and C. Yeah, the same thing we will talk about here only. Okay. So it gives the concept of temperature. For example, consider two systems A and B separated by a adiabatic wall. Adiabatic wall. Okay. Place a system C in a contact with A and B via conducting wall. Like A is connecting with C, B is also connecting with C, which means A and B are in a thermal equilibrium So A and B are separately in the equilibrium with C, so that temperature of A will be equal to temperature of C, temperature of B is equal to temperature of C. If I consider this as equation 1, so equation 1 and this as equation 2, so TA equals to TB, we can write now the same thing, right? So I can say the temperature of A is equal to temperature of B when temperature of A is with contact with C and temperature of B is contact with the C. So I can say that A and B are in thermal equilibrium. Got it? Now, heat, internal energy and work. What is the meaning of that? We will see. So usually, like many of you guys have confusion about what is the temperature and what is the heat. Temperature and heat both are different quantities. Try to understand the thing. Temperature will give the hotness or coldness of a body, but heat is nothing but is an energy. Okay. So temperature determines the direction of flow of heat when two bodies are placed in thermal contact, whereas heat flow from a body of high temperature to the low temperature. Got it? So direction of flow of heat when two bodies are placed in thermal contact, and heat is nothing but it is flowing from high temperature to the low temperature, always, okay. So what is internal energy? Meaning of internal energy. So the sum of molecular and kinetic energies, kinetic energies and potential energies in a frame of a reference related to which the center of mass of the system is at rest. So the internal energy is denoted by the U, letter U, and the internal energy depends upon the state of system. So these 2 points are important. Okay, got it? Next one. Yeah, we'll go for the thing here. So how we will calculate it? So for example, if we take a system here, okay, like it's filled with gas. I'm applying a force. So we'll be having some area, and force is nothing but pressure into area. We can take it, right? Pressure into area. So I'm applying some gas and I'm pulling, like I'm applying some force and I'm pulling out. So which means it has been displaced into dx distance. Okay. Now, see, gas does work on surrounding with positive. Work is done on the gas is negative. Okay. Gas does work on surrounding is positive. Work is done on the gas is negative. Okay. If a gas is compressed, piston pushes the gas inward work. If a gas is expanded, it pushes the piston outward. Okay. See here. So we know that force equals to pressure into area. And work done is equals to F dot S or Fs cos theta. Right? We can write like this. For small work, the small displacement will be happening. For small displacement, small work, na? Yes. So for small displacement, small work done has happened. So force I can replace with the pressure into area and into dx. What is the meaning of this? A into x, which is nothing but gives volume. A is nothing but x into x, no? Like displacement into displacement, like length into length, volume. So I can say that from 0 to W, and this is from V1 to V2. Got it? V1 to V2. So from this we can understand that if volume doesn't change, work done will be 0. If volume work done is 0. So meaning that area under a curve, the equation of gas, work done by a gas equals to area under PV curve, pressure and volume curve. Okay, if gas is expanding, work done is positive. If gas is compressing, work done is negative. Work done is negative. So this is the basic idea about the calculations. Okay, and you can take this equation and we can go for the next one. Got it? Okay, done. So if we talk about here important condition like a quasi-static process. Quasi-static is nothing but it's a slow process, we can say. Slow process. So this formula works only when the process is very slow. Yes, as I told, it's a very slow process. So the system remains in thermal equilibrium. Such slow process is called as quasi-static process. Quasi-static. Okay. Now, when a gas expands slowly from V1 to V2, the work done by gas is represented by the shaded area under PV curve. Okay, so the shaded area is there. No, will the shaded area will gives me the work done. Gives me the work done. Okay, suppose if volume is constant, what about the work done? Work done is 0. Work done is 0. Got it? Got the point? Okay. So work done depends on path taken. Yes. So the same initial and final state can give the different amount of work depending on how the gas is going from one point to another point. So here we are taking a graph from point A to point C. I need to travel. I can travel by A, B, C. I can travel directly A to C, or A, D, C also I can travel. Right. So path AC gives isothermal. So like we'll discuss about the graph upcoming. Okay. So isothermal, and ABC expands at a constant pressure. Okay, constant pressure. Then cools at constant volume. Okay. So here the work done will be nRT log V2 by V1, and along ABC, AC is like it's a isothermal, we have talked. ABC like P1 is constant and V2 minus V1. P1 is constant and then V2 minus V1. Got it? So these values are not equal even though both starts at A and end at B. So hence thermodynamic work is path dependent. So this is the main point. It is the main point. So thermodynamic work is path dependent. So if you see here some examples we have given, and you can take this tabular column, it will be very useful. So type of process: isothermal, isobaric, adiabatic. Okay, and equation for gases, equation like work done: isobaric, adiabatic, isothermal. Isothermal, temperature is constant. Isobaric, pressure is constant. Isochoric, volume is constant. Your pressure, your temperature, and adiabatic, heat. No heat exchange, na? Okay. constant, pressure constant, volume constant, no heat exchange. So if you see work done nRT ln V2 by V1, isobaric work done is equals to P into V2 minus V1. Isobaric when volume is constant V2 minus V1 is same, so it is 0. And adiabatic P1 V1 minus P2 V2 by gamma minus 1. Okay, so if we talk about a cyclic process, clockwise will give positive, anti-clockwise will give negative. Okay, clockwise will give positive, anti-clockwise will give negative work done. If you talk about here, yes, there is a this one is like this. Okay, so it's anti-clockwise negative, clockwise positive, anti-clockwise negative. Okay. Done? Okay guys. So if you talk about the speed, gradient, dissipation, path in state space, entropy generation, work output, heat engines. Okay, so speed infinitely slow. Okay, for quasi-static, like reversible and irreversible, we are talking reversible and irreversible process. Okay, we are talking about reversible and irreversible process. Okay, so when I talk about a reversible process, speed is infinitely slow, irreversible, final and fast. And the gradient, if you see, delta t tends to 0, delta p tends to 0, delta mu also tends to 0, and it's a finite. Okay, so dissipation, like no friction, viscosity, resistance, like friction will be there, turbulence will be there, joules, heating, inelasticity, everything will be there, and it's a well defined continuous PVT path, and jumps are it is indefined during the path. Okay, and like S gen, like entropy will be 0 and entropy will be greater than 0 here. So output is maximum possible less than the reversible. So ideal or cannot limit real engines. Okay, real engines. These are the difference between reversible and reversible process. Okay. Next one, if you see first law of thermodynamics. So if you talk about first law of thermodynamics, what are the things are available? Delta Q, delta W, delta U. So delta Q means heat supplied to the system by the surrounding. Delta W work done by the system on the surrounding. Delta U change in internal energy of the system. Okay. So according to the law of conservation, no. So delta Q is equal to delta U plus delta W. Okay. So work done by a system against a constant pressure, which is nothing but delta W is equal to P into delta V. So for constant pressure we are talking. Constant pressure. So what then I can replace it as P into delta V. Yes, this is one of the important point when we talk about problematic point of view. Okay, sign conventions. So delta Q is positive when heat is supplied to the system. It is supplied to the system. Negative when heat is rejected. Delta U is positive when temperature increases. Delta U is negative when temperature decreases. Delta W is positive when work done by the system, and W is when W is negative, work done on the system. Okay, so delta U depends only on the initial and the final state, it does not depend on the path taken. Okay, does not depend on the path taken. Yes, so here is the one of the question. A gas is compressed from a 10 meter cube volume to 4 meter cube volume at a constant pressure of 50 Newton per meter square. Then the gas is heated by giving 800 joules of energy. The internal energy delta Q is equal to delta U plus Is that thing no? No. Yes, delta U plus delta W. What is work done? Work done, I can say that pressure. Work done is equals to pressure into delta V. So delta Q is equals to what is delta U? Internal energy I need to find. So delta Q, how much they have given? It's a 100 joules. 100, right now. So one more thing, like constant pressure, like internal energy of a gas, okay, heat, gas is compressed in the sense work done will be negative, will be equals to delta U minus what is the pressure 50 and what is the volume 6. So 10 meter to 4 meter it has been kept, 6 is the remaining thing. So 100 is equals to delta U minus 300. So delta U will be equals to 100 plus 300, which is nothing but 400. Option increases by 400 joules. Option 3 is the correct answer for this question. Option 3 is the correct answer for this question. Right? So next question. A gas expands 0.25 meter cube at a constant pressure. Gas expands, they are saying. Expands. So expanding, like volume they have given, pressure they have given 0.25 into 10 power 3. So 0.25 into 10 like 1000, no? So 20 is 250 Newton or joules? Yes, joules. Newton in the sense it's a force. Watt, joules, energy. Urge. It is CGS unit. SI unit I need to get it. Thermodynamically system goes from one state to another state, the external work done will be. So here if you see, pressure is changing. Pressure is changing. Volume is constant. So when I write the formula, P into delta V, pressure I can take, okay, P2 minus P1, okay, fine. What about volume? Volume is constant. So volume constant in the sense V2 minus V1, V2 is equals to V1. So it will get cancelled. So something multiplied by 0 becomes 0. W is equals to 0. So work done is 0 here. Work done is 0 in this case. Next question. So thermodynamical system goes from state A to B, shown in the given figure. What is the work done? Pressure is constant, so P. Volume is changing, 2V minus V. So answer is PV. So option 1 is the correct answer for this question. So in indicator diagram shown, the work done along path AB. Work done along path AB they are asking. So work done path AB, only AB. So only AB in the sense 20 is the pressure, volume is 1. So answer is 20 joules. Like it is increasing 20 joules. It's not minus 20, it's a 20. Okay? If the arrow mark is given in this direction, I need to take 3 minus 2, which means, yeah, so minus 2 minus, 2 minus 3 we should take. So its answer will be minus 1. So minus 1 into 20, I'll get minus 20. Got it? Okay, so the next one is the final question we'll see in this class, and we'll discuss the upcoming question in the next session. A gas of a given mass is brought from a stage A to B in how many directions? 3 directions. Okay, so as shown in the given figure, the amount of work done in this process respectively. So when I talk about this now, like let me take the points towards down. So area of this one, first one, then area of the second one, and next area of the third one. So if I talk about the area, no, area of the first one, second one, third one. Third one is greater, second one is less than third one, and first one is less than first, so third and second. So 3 will be greater than 2 will be greater than 1. Option 2 is the correct answer. Option 2 is the correct answer. Yes. So with this, I'll end up this session, guys. I hope it's clear. We have done like some questions in this topic, and we'll